What if I told you that the models powering tools like Google Translate and ChatGPT got a revolutionary upgrade, all by throwing out their most fundamental building block? For years, the state-of-the-art in understanding language was dominated by recurrent neural networks, or RNNs, but they had a critical weakness. Today, we are breaking down the paper that changed everything. Attention is all you need. We will see how its authors replaced recurrence with a powerful concept called attention and unleash the architecture that defines modern AI, the transformer. So what was wrong with RNNs? Models like LSTMs and GRS were the champions of sequence modeling. They processed data like a sentence, one word at a time. The hidden state at time t is a function of the hidden state at t-1 and the new input. This creates a chain of dependencies. You cannot read the fifth word until you have read the fourth. This inherently sequential nature is a huge problem. It prevents parallelization. For very long sequences, this makes training incredibly slow and memory intensive. The authors of this paper proposed a radical solution, the transformer. It is a model architecture that completely eschews recurrence. It gets rid of that sequential chain. Instead, it relies entirely on a mechanism to draw global dependencies between words, no matter how far apart they are. That mechanism is called attention. This one change unlocked two massive benefits. First, significantly more parallelization. The model can look at all the words in a sentence at the same time. At a high level, the transformer follows a standard encoder decoder structure, which is common in tasks like machine translation. The decoder's job is to take that representation Z and generate the output sentence, one word at a time in the target language, say German. It is auto-regressive, meaning to generate the next word it looks at the words it has already generated. Both the encoder and decoder are built from stacks of identical layers. Each layer has two main sub-layers, a multi-head self-attention mechanism and a simple feed-forward network. An attention function is like mapping a query and a set of key-value pairs to an output. Imagine you are translating a sentence. To translate the word "it," you need to know what it refers to. You compare your query to every key to find which words are most relevant. This compatibility score is used to create weights to take a weighted sum of all the values. The transformer uses a specific type of attention called scaled dot product attention. We compute the dot product of the query with every key. This is our compatibility score. A higher dot product means more similarity. We scale these scores. For high-dimensional keys, the dot products can grow very large, pushing the softmax function into regions where its gradients are tiny, so this scaling factor keeps things stable. The softmax function turns these scores into probabilities or weights that sum to 1. The most relevant words get the highest weights. Finally, we multiply these weights by the value vectors to get our output, a representation of the query that pays attention to the relevant parts of the input. Instead of performing just one attention calculation, the transformer does it multiple times in parallel. This is multi-head attention. Think of it this way: instead of one person reading a sentence to understand it, you have a committee of 8 experts. Each head receives a slightly different learned projection of the query's keys and values. They each perform the scaled dot product attention in parallel, focusing on a different aspect of the sentence. After they are done, their outputs are concatenated and projected one last time to produce the final result. This allows the model to jointly attend to information from different representation subspaces. With just a single attention head, this fine-grained focus would be lost due to averaging. In encoder self-attention, the query's keys and values all come from the output of the previous encoder layer. Every word can attend to every other word in the input sentence to build a better representation. In the decoder, we apply a mask to preserve the auto-regressive property. This ensures that the prediction for a word only depends on the words that came before it. In encoder decoder attention, the queries come from the decoder, but the keys and values come from the output of the encoder. This is the crucial step where the decoder looks at the entire input sentence. How does the transformer, which looks at all words at once, know the order of the sentence? The cat sat on the mat is very different from the mat sat on the cat. The solution is positional encodings. Before the word embeddings are fed into the first encoder or decoder layer, we add a vector to them that represents their position. The paper uses a clever trick with sine and cosine functions of different frequencies. Because of the properties of sine waves, the model can easily learn to understand relative positions. So why is self-attention so much better than recurrence or convolution? The paper highlights 3 key advantages. The number of sequential operations for a self-attention layer is constant. An RNN requires O of n operations, where n is the sequence length. It must go in order. To learn the dependency between 2 distant words, the signal in an RNN has to travel through every single word in between. In a self-attention layer, the path is direct, which makes learning long-range dependencies much easier. It even generalized to other tasks like English constituency parsing. The transformer was not just a new model, it was a new foundation. By replacing sequential recurrence with parallel self-attention, the transformer architecture solved a fundamental bottleneck in AI. It allowed models to be trained on vastly more data far more efficiently. This brilliant combination became the blueprint for nearly all modern large language models, from BERT to GPT-4. So the next time you use an AI tool that seems to understand language, remember the revolution that started here with one simple, powerful idea: attention is all you need. Thanks for watching. If you want to dive deeper into the papers that shape AI, be sure to subscribe to BlackboardAI. See you next time.